Cool. So now let me introduce you to our speaker of today. So I'm really pleased to introduce you to Maximilian Parzen, who is a second year PhD student within the University of Edinburgh in IS. So Maximilian is going to present us his research about data science mathematical optimization on a energy storage facility. So Maximilian, whenever you're ready, look forward to your talk. Thank you.
All right. Thank you very much for this great introduction. Can you see my screen?
Yes, all good, yeah.
All right. Yeah. My name is Max. I'm a second year PhD student, and I was working until recently, like on this preprint, which is hopefully published soon. And yeah, the whole thing about my research is to improve energy storage. But I think the type of analysis I'm doing is also suited for some of the IES colleagues, and that's why I'm presenting here, just to share with you my experience, and maybe we can find also ways to collaborate in future. So, like, we're starting today with costs. So there's like a kind of a cost figure here, which you can see on the screen. It's like a levelized cost approach for storage specific. And it's similar really to that levelized cost of electricity, which many of you are maybe familiar in terms of generators. But for storage, it's also like quite similar. So it's like all the discounted cost is like summed up and divided by the kind of a usage factor. And what usually comes into this cost factor is like assumptions about the storage design is often fixed. And then there's also like a kind of charging price, which is fixed, or sometimes represented in time series, and also some kind of assumptions of full load hours. And yeah, what usually, like what people are arguing about that is like there are fantastic studies with the levelized cost approaches, and in terms of storage, for example, they're actually saying that this type of studies gives transparency around future competitiveness of electricity storage, and it helps guiding research policy and investment. So like really like impactful research, like one can think about, right? And yeah, there's some also like more sophisticated analysis, and they also talk that, okay, one storage can outcompete the other one because of like some special levelized cost figures. And that's not like in like low journals, it's like in impactful journals where this is published true. So like just to give you a perspective of who might be interested in some kind of factors, like to see, okay, what kind of technology is competitive, is first like a kind of asset operator. Could be also, if you look like more in the future, the project developer who's interested in that, the system operator, which is like sometimes also operating the market. For example, in Germany, the TSO is doing that. Yeah, then the regulator is also interested in such kind of studies, and they derive from their like future like investment or R&D budgets, and also the manufacturer. So whatever the manufacturer is developing in the R&D department depends really on a quite of a assessment. And like what I saw recently is that these assessments or how they choose technologies often also based on some kind of cost figures, like the LCOS, for example. And yeah, if you look more in the past, historians might be also interested, or actually, like if you do backcasting with energy system modeling, yeah, some kind of modelers might be also interested in the past. The key message of today is that lower cost is not equal to higher value. And it really, like, I analyze it just for energy storage, but there are some also like studies about it in terms of wind turbines. Like, I'm aware of an IEA study, and it should be for all kind of other assets, like demand response assets, or whatever other generator we're talking about. So what we define as valuable is like energy technology that lowers total system costs. And yeah, like, it actually makes sense, right? Like a technology which somehow reduces the energy bill costs at the end. It's like a good technology. Like that's something we should strive for. And one tool to assess that are like energy system models. But like, I think not every model is suited, and like what we should really aim for is some kind of models that are based on real data. And like what I mentioned here is like, okay, the aim in the future is like just building like a digital twin. So based on like realistic power plant data or existing power plant data, which usually comes from geoinformational, from geospatial information. That's something which the model should be based on over larger areas, or in the best case, the world. For example, a manufacturer would be interested to quantify the value of this technology in the world market, right? And like, there's one model like I'm using, it's like Pipes Euro. We talk later about it, but that's really something where like what you can imagine as a digital twin. Now some advertisement, like we're starting in May our Earth mission. So we're building an open energy system model in Africa, and expanding like this European model you just saw before. And we think that we can finish that model expansion before end of this year. So, and like currently I'm leading this team, and we are at the moment like 9 people from mostly PhD students, part from Edinburgh, and also some people from Norway, Germany, and US. You can also get some more information like on my GitHub website, and see some more details about the project. Yeah, so energy system modeling. What is it? How does it work? So usually what this kind of models are doing, they're minimizing cost. And so what they're doing is like looking at investment costs, like summing them up for all the locations, and also reducing the marginal costs, like the operations. And yes, that's also subject to constraints. So we're adding basically the physics to it to make it kind of realistic, right? So that demand must match the supply, that the wind and solar potentials are not like unlimited at one location. Like I cannot place like millions of turbines just in Scotland. It's just not possible. And that's how we basically constrain like the models to gain some kind of realistic outputs. And now just an introduction to Pipester. So Pipester is a workflow to build a model from open data. And what we're doing in Europe is like we're collecting a lot of data from power plants, also the existing NSOE power lines, which are planned and also installed. We have time series for electrical demands, and then, for example, also deriving a time series for wind and solar. And it's also restricted in terms of geopotential. And that's how we basically come up with this kind of maps. And in this case, I'm actually looking on a future scenario with 100% of CO2-free technologies. So now to make it a bit more clear, like also sharing our research from our department, basically on energy storages. We are counting in this case study just values from energy arbitrage and seasonal resource provision. So not this really short time services where energy storage can also provide some values. But it, of course, can be included in future with different techniques. So what we did is like we compared like hydrogen storages, which you have usually a charger, which is called electrolyzer, a discharger, which is called fuel cell in terms of hydrogen, and then you have also like a kind of hydrogen tank. And we added like for all these components like a low cost and a high cost scenario, an LCOS scenario. So you see like the kind of factors are different, like that's like the input parameters. Yeah, and we also added like a battery inverter, which is based on lithium-ion battery, just to have a kind of baseline. And what we saw is like, okay, this low LCOS case has like, with a set of assumption, I told you, like you must always assume something, has a cost of 21 cents per kilowatt hour. The high LCOS case has 26 cents per kilowatt hour, and the battery got like 10 cents per kilowatt hour. So like if you just, if you're just judging about LCOS, you would clearly say, yeah, battery is the best case. Okay, but now people know, yeah, hydrogen storage, you're using that for a different case. So they say, yeah, it has also its own market, right? But if you compare two hydrogen technologies, okay, which is now the better kind of technology? And that's like key to know for manufacturer or whoever is using hydrogen units. So here you would clearly say, okay, they have the same purpose. Of course, they go for the low cost version, right? Yeah, but what we showed is that this is not the case. So first of all, like what I'm showing here is like a LCOS on the y-axis, and here you see the three different technologies. The kind of bubble size, like what is this bubble? I showed you previously this map of Europe, right? And we had like 181 dots in this European map. So we optimized something, received some capacity out of that. And this capacity indicates that this kind of technology helps to reach the minimum cost in the system. So it basically shows that all these bubbles here, that's basically the optimized capacity, okay? And it also shows like the kind of different full load hours, which is this color degradation. And what we see is like a single LCOS is not really like a good assumption. Like we have a wide range in all kind of technologies. Then, yeah, assuming one constant full load hour is also quite dangerous. Like we have also a pretty wide range for all kind of technologies. Yeah, and like what was striking in that case is like, okay, yeah, okay, what is now the better technology? Is it the low cost version? But somehow we have for low cost and high cost technology a market potential, right? So that indicates that actually both technologies are valuable. So why we are assessing the LCOS? And this kind of, like, we basically said, okay, maybe we should focus on the kind of quantity which we receive out of the optimization, and focusing more on this stuff and also analyzing it systematically. So that's where we come up with the market potential method. It's like just a systematic approach to analyze the quantity of our optimization results. And yeah, first of all, we have this market potential indicator, which is just the size of the optimized volume. And we say, okay, we need a probable scenario, and a result could be, okay, a certain quantity. And the market potential indicators just from this 181 nodes, the aggregated amount, so really all the volume which is optimized. It could be for wind turbine, charger, or whatever technology. Okay, scenario selection. What is a probable scenario? That's maybe also a good question. And we say it's like one that's likely to be happen. And yeah, we used it in this case just a deterministic approach, right? Not some kind of stochastic simulation, but like one can argue that, okay, whatever the NSOE, like a central association, is deciding for, that's maybe something which is kind of the way, which is a likely scenario. And they're using 3 scenarios, so maybe we should also go for something like that. And then there's the market potential criteria. And that's basically simple. If we have a market potential which is 0, it's unlikely to be a valuable technology. If it's larger than 0, it's likely to be valuable. If it's larger than 0 in multiple scenarios, it just reduces uncertainty. And then there's also some additional rules, like companies could apply. For example, if Siemens wants some kind of specific minimal market, then they can exclude, for example, like to a specific threshold, all kind of technologies below that. And then, yeah, bigger market is better. I think this is self-explaining. Yeah, and basically, if we check like the numbers in 3 different scenarios, it's not now related to the NSOE scenarios, but we show 3 different scenarios where we changed a bit the design constraints of the energy storage. What we actually saw is that some of the high LCOS components are more valuable than the low LCOS components. So that was like one surprising result. Yeah, and it also, there's some more details on that, which you can find in the preprint. But it suggests really the result that higher costs technology can be also more valuable. And then also the LCOE is like a kind of incomplete measure, right? So why is this the case? That's maybe what many people are asking now. And we have some reasons. And like the difference is maybe like the spatial temporal energy system characteristics, which is like completely different from location to location. So different resource potential, demand profiles, network structure. Then I have for each of these locations like different power profiles as well. I have different design flexibility constraints for the components. I have different efficiencies for the components, and also different investment and operational costs. So all these factors, and combining like the focusing especially on the components, can lead to this like special case that low cost is not a higher value. Yeah, and like just the market potential, why it's maybe a useful approach. Like we use endogenous variables to quantify the value. So that's good when a lot of is changing, and in the future maybe we have sector coupling or other kind of impacts, which we can also show in like energy system models, and we can account for these changes. And we also acknowledge, because we're building a digital twin, basically, we can also acknowledge for the spatial temporal difference in the energy system. And like this kind of technique also overcomes some limitations of alternative approaches like the cost profit or some other system analysis approaches at Imperial College. Yeah, so there's more on that on the preprint. So I'm hitting my time limit. Yeah, so yes, modeling can always improve. There are some points which I mentioned here. There's something for afterwards. Key takeaways is, okay, we have a problem that lower cost is not equal higher value. The aim is that, yeah, we want to design actually technology to reduce the bill, to be profitable for industry. And that's actually not a conflict at all. And the solution could be, for example, the market potential method that helps like guiding like energy technology innovation, so on which path to go. And now, like I also took some time to thought about, okay, where could this method or this modeling framework help IES? So there are, in general, the possibilities to give design, like technology design recommendation for whatever technology, like could be a storage, a generator, or demand response. And I thought especially on, wave converters or similar technologies, which are often like considered as more expensive technology, but maybe the kind of special power profile brings some kind of values at certain locations. Maybe it's not the case in UK, but maybe it's like in Africa, like a special profile which is helpful in the power system. That's something we can see with that. Yeah, and then we can also evaluate the energy technology market potential. So what is the system value of a technology, and also roughly the market size. Like the IES could also support the tool improvements. And I mentioned that, like I think two weeks ago in a presentation, like it would be really nice if we could add like some kind of water flow velocity maps to include endogenously the marine potential better. I think a water depth resource map to constrain like the offshore wind technology would be also helpful. So distinguishing if like a technology is based on a pile or as a offshore floating technology. So maybe there's a cost difference, I'm pretty sure. And there's also the opportunity to add concentrated solar power. Is not yet included in this model, but maybe someone is interested to contribute in this. And like I also have some kind of example research ideas. Like we could compare like low wind and high wind turbines. That's like I saw that in an IEA study, but I think with this approach maybe that's a nice extension. Yeah, and we can also focus on tidal and wave converters. And yeah, that's me. That's something you can contact me about. Write me in wherever, LinkedIn, GitHub. Maybe you can check my website out for the Pipes of Africa project. And yeah, I'm happy to help or give any kind of information. Thank you.
Thank you very much. Very good presentation, very interesting. So yeah, kind of hear myself as an echo for some reason. So
are you here in echo?
That's
it's better.
That's okay. So we'll be happy to. I think Max will be happy to answer any of your questions. If you want to just raise your hand and ask questions. Yes, David.
Thank you very much for a very interesting presentation. That was really good. It would, as you say, it would be very interesting to see what this means for some of the other renewable energy technologies that have been being developed, and in particular, Brian and I were involved in a meeting about a tidal project that we're involved in this morning, where someone was presenting a whole load of information based on how do we get the levelized cost of energy down.
Yeah.
And maybe the important message to get out to people is maybe you don't have to.
Yeah.
But the question is, how do we make sure that the policymakers and the politicians who have been sold the idea that a low levelized cost of energy is absolutely the gold standard, how do we get them the message that maybe that's not the case?
Yeah, that's a great question, and I think that's like I think a year ago maybe the same questions like that one like Harry asked me that. And like I wasn't sure how to answer that, but I think now my answer developed a bit. I think like all of our technology operates in a market, and like the market won't work in future as it works now. Like we have a lot of kind of marginal costs close to zero, right? And I think maybe the market will indicate this by itself, because, for example, if we produce, like, we have a demand of 50 gigawatts. If we produce like 100 gigawatts, we just simply don't need the other kind of gigawatts. So it's like kind of wasted energy. And if a technology provides like over the time better energy at the right times, then it can be more valuable. And that's also what LCOS cannot show, but it's what the market potential method could give a clue before the technology is not making any money anymore. Yeah, but in general, yeah, market operation also depends on regulation. So getting this message out maybe might also help a bit. Yeah.
Thank you very much.
Yes, James, you can go for it.
Oh, hi there. Thank you.
Yeah.
I was wondering, Max, if you could tell us, in the kind of lowest cost energy future, what is the mix of technologies that you see, and how does that change if there's a net zero constraint imposed?
So yeah, like I had my slides there. Maybe I can just share them so we can roughly see what is the distribution. So obviously, like in this work, we didn't aim for the most realistic future. Like there are many things you must be more careful about. That was not the aim. We just wanted to show this kind of case. But what we can do here, yeah, like what we saw is actually that kind of wind is really attractive in the northern part of Europe. In the southern part, it's more solar, but also wind helps also in certain locations. Yeah, like, but of course, like in this this optimization, you need to be a bit careful. That's what we saw, and like, you know, there's also many constraints you can add. We added like a self-sufficiency constraint, so it means like that at least a country wants to produce 70% of its own energy demand in its country. So that's why we actually see that all of this country have some kind of generators installed in the future. And depending on where they're located, it's like a different kind of technology, what you can see. Yeah. Thank you, James, for this question.
Thank you.
I think there was a question from Harry as well.
Yeah, it's not really a question. I just want to follow on David's point about policymakers. Of course, in the UK, the big issue here is that renewables get contracts for difference, which incentivizes them to go for the lowest cost solution because the revenue that they get is fixed. So maybe the first step in trying to convince policymakers that something like tidal, which might have a higher value to the system, should maybe be supported in a different way.
Yeah, good point, Harry. There was also like, I'm not sure how this is exactly implemented in the policy world, but I know that Leon Hurt, like a economist in Berlin, he talked about it as well, and he said that there's some kind of special policy measure which actually doesn't focus only on costs. I'm not sure how it works in detail, but there are like certain developments, and at least I know that something like this is somewhere implemented. Just follow Leon Hurt. I'm just writing that down in the chat, so maybe you can get there some kind of ideas.
Thank you, Max, and yes, thank you everyone for asking these very interesting questions. We still have time for more questions if you'd like to.
Sure. Yeah. Okay, James.
I could probably ask questions all day. So I was wondering if you've thought about different ways of transporting energy, particularly with hydrogen pipelines or ammonia shipping.
That's a great point. So that's something we can include in models as well. Like we have, for example, with this model, the possibility to include like pipelines, some kind of work who already tried to do it. Yeah, like I think, yeah, like I'm not really aware how that works in detail. Then it's possible. I know some guys in ETH at Zurich. They're working on that. Rubinios, I think he was exactly discussing about this point. Yeah, it's just simply someone needs to make the effort to include like sensible assumptions to a model like this. Yeah.
Thanks.
Okay, well, yes, thank you very much, Max. That was a very, very interesting talk. Yeah, learned a lot today. Thank you for this. So I will, just